Hey everyone. In this video, we're going to talk about the pH scale and some indicators and look at the math behind calculating some of this stuff. So most of you are probably at least a little familiar with the concept of pH. Here's a scale on the screen, and we can see the pH generally, the scale, we put it from 0 to 14. Now it can go beyond both of these numbers. You can have negative pHs as well as pHs above 14 when you have very, very strongly acidic or very concentrated acids or bases. With the pH scale, a pH of 7 is considered neutral, which is pure water. Below 7 is considered acidic, and the farther below 7 you go, the more acidic it becomes, and above 7 is considered basic. So we're going to look at the details of how this scale is made, as well as some other math that goes in behind it and behind the calculations of pH and concentration. But before we do that, in the last video we ended off looking at a titration very briefly, and I mentioned that you need an acid-base indicator when performing acid-base reactions. Okay, and that an indicator allows us to tell when a pH is changing to a certain number. Okay, so it's a measurement of pH. So let's take a look at a few indicators first and how we can actually measure this pH if we have an unknown solution. The first indicator, or a very common one, is litmus paper. So all litmus paper does is it tells us if a solution is acidic or basic. So when you touch the paper to something, if you take litmus paper, if you take blue litmus paper and you touch it to an acid, it will turn the paper red. And if you take red litmus paper and touch it to a base, it will turn the litmus paper blue. So again, you can remember blue for base. Okay, and then the other option would have to be acidic, so red for acid, and blue for a base. So it doesn't really distinguish individual pHs, but just tells us if we're dealing with an acid or a base. Getting a little more selective and specific is we have universal indicator or pH paper. Okay, so here the scale that you see at the top. So we have a pH from 1 to 14, and each pH the indicator will change to a different color, starting at red when we have a very strong acid, moving up through green in the neutral area, and then to purple when we have a very strong base. So the universal indicator is a liquid solution. So in the image below, you would add the universal indicator into your solution, and then it would change to a particular color. Okay, in this case, we see a solution. They're matching it up with the scale, and we see that it's at a pH of 6.5. pH paper is a similar idea, except it's just in paper form, but it still has all of the different pHs from 0 to 14 or 1 to 14. But it's just a piece of paper that you dip into your solution and you can see the color change. So here's a chart. This just has a few different common indicators that we'll see as we do labs and whatnot. So bromophenol blue, methyl red, and you can see the different colors they change. So for example, if you were to choose methyl red, if you're looking at something that's changing from a pH of 2 to 5, so in this area, methyl red's not very useful because the color stays fairly consistent. Or if you have something that's changing from 6 to 10, again, you wouldn't really want to use it. But if you have something going through a change, if you have a reaction and you know the pH is going to change around 5 or 6, then methyl red would be a great option to use, as it's a very drastic color change. So if we're switching from an acid, a base would change around 7, but if we're switching from something from a pH of 5 to 6, or lower than that to something higher, if it's passing through this point, then we can use methyl red as an indicator. That's why we use phenolphthalein. So phenolphthalein, that changing point is around 8. So when we do titrations, when we're looking for the neutralization point, phenolphthalein is a great one to use, as we'll change from either pink to clear or clear to pink depending on which direction we're titrating. So each has its purpose, and it's a certain situation you would use it. And we'll go more in depth in this when we look at the advanced part of acids and bases, and do more in depth with titrations of weak acids and weak bases. You can also have natural indicators. So a great natural indicator is actually red cabbage. So if you boil down, or if you take red cabbage, put it in a pot with water and boil it, you can extract the pigment out of it. And that pigment, putting it into different solutions, actually causes it to change color based on the pH. So we can see here that it goes from a reddish color through the pinks and then into a green color when it becomes strongly basic. So a lot of foods that we eat are actually natural, have natural indicators in them. Blueberries, you can use tomatoes, right? And each would have its own set of colors it changes to depending on what's causing the pigment in that particular fruit or vegetable. But the best way to distinguish pH is using a pH probe. Okay, so a pH probe it uses we'll learn more about this when we study conductivity, exactly how it works. But essentially, you just dip it into your solution. It detects the amount of hydrogen ions that are in the solution, and based on that, we'll put back a pH reading on a screen. So this one is you get a very specific reading. You don't need additional indicators. You just need the probe. So, well, they're much more expensive than indicators. They are much more specific. So if you're doing analytical chemistry, you would want to use a pH probe. Okay, so that's a bit about how to test for what the pH is. Now, what exactly is pH, though, and what does that mean? So pH is just a simple way of representing the concentration of hydrogen ions in solution. And remember we talked about before hydrogen ions, which we also refer to as protons. Okay, we can also just refer to these as hydronium ions as well. They are equivalent when in solution with water. So the pH, again, is just a way of representing the concentration of hydrogen in solution. Now, the concentration of hydrogen in solution is usually quite small. So the pH is a log scale. So to calculate the pH, we find our concentration of hydrogen in the solution, and we take the negative log of that. Okay, and that converts it to a scale that's generally from 0 to 14. So it just makes it a little more simple to read. And the reason we do that is the hydrogen ions in a solution generally range from about 1, which would give us a pH of 0, to 1 times 10 to the negative 14, which gives us our pH of 14. So that's why we put this on the log scale. We can also use pOH. So it's the same thing except when dealing with a basic solution. So instead of looking at the hydrogen ion concentration, we look at the hydroxide ion concentration in solution. But it's the same calculation, but it will give us the opposite scale. So a strongly basic solution will have a high pH, but a very low pOH. We'll see that on the next slide. You may be asking yourself, what does P in pH mean? H is kind of obvious. H stands for the concentration of hydrogen, or OH for the concentration of hydroxide. But what does that P mean? Some people claim that it stands for power, but I haven't been able to find any definitive proof that this is what it originally stood for. So really nothing. It's just a letter that we use to signify we're taking the negative log of something. So P, in a sense, kind of just stands for the negative log. For example, remember when we did equilibrium constants and we did our Kc? Well, an equilibrium constant for an acid is a Ka, and eventually we're going to study in the advanced section something called pKa, which is literally just the negative log of your equilibrium constant for an acid. Okay, so P, again, kind of just stands for taking that negative log. Now with pH and pOH, so here's our chart. Now we know that 7, okay, this is neutral. So at 7 we have a neutral solution. And if you look, the concentration of hydrogen ions and the concentration of hydroxide ions are equal. Okay, 1 times 10 to the negative 7 and 1 times 10 to the negative 7. So the pOH is also 7. If we go up a step in pH, okay, so let's say we get slightly more acidic, so we go to 6, you'll notice that this is a 1 times change in pH, so an increase by 1, I should put plus 1, not times 1. So, or if we subtract 1, that is a 10 times increase in the concentration of hydrogen ions. Again, so if we go up 2 steps from 7 to 5, okay, that is a 100 times increase in the concentration of hydrogen ions. So each step in pH represents a tenfold change in concentration. So when we're moving up 1 pH, we're not getting twice as more acidic, we're getting 10 times more acidic. And that's why things can get pretty dangerous when working down in those low ranges or very high ranges of pH. Something else you might notice, so if we have a solution that has a pH of 14, for example, then the concentration of hydrogen ions are 1 times 10 to the 14, and the concentration of hydroxide are 1 times 10 to the 0, okay, or just 1. If we have a solution of 13, we have these concentrations, and you notice the POH at a pH of 14, POH is 0. At a pH of 13, the equivalent POH is 1. So we can come up with another equation here. The fact that the pH plus the POH is always going to be equal to 14. Okay, we'll look in a little bit where that comes from exactly. So let's take a look at a few examples. So our pH calculation, right? pH is equal to negative log of the concentration of H. If we rearrange that, we get that the concentration of H is equal to 10 to the negative pH. Okay, so we're just rearranging using our log rules that you would learn in math to rearrange the equation if we need to solve for concentration. So in this first example, an acidic solution has a concentration of hydrogen ions, or protons, of 2.50 times 10 to the negative 3 moles per decimeter cubed. Calculate its pH value. Okay, so an easy one here. We know our pH is the negative log of the concentration of hydrogen ions. Okay, we're given our concentration of hydrogen ions in the question. So this is just a question where we need to fill in our information. Times 10 to the negative 3. Okay, and that gives us a pH of 2.60. And there's no units associated with pH as we are taking the log of the number, so it is a unitless quantity. Okay, so we're dealing with a fairly acidic solution in this case. In the second one, we have calculate the pH of a 0.02 molar per decimeter cubed solution of nitric acid, HNO3. So we're not given our concentration of hydrogen in this case. We're just given our concentration of a strong acid. But an important thing to know is that the concentration, when we're dealing with a strong acid, we're going to get to this in the next lesson, but a strong acid will 100% dissociate in solution. So the concentration of your strong acid will be equal to the concentration of your H plus in the solution. Now that assuming that we are dealing with a monoprotic strong acid, which in this case we are. If we were dealing with a diprotic one, then we may end up having to double the concentration of hydrogen. But in this case it is equal. So that means our concentration of hydrogen is equal to 0.0200 mole per decimeter cubed, or molar solution of hydrogen. So now we're just filling that into pH again, minus the log of 0.0200, and we get a pH of 1.70. Okay, in this last question, calculate the hydrogen ion concentration of a solution with a pH value of 5.3. So in this case, we're using our rearranged equation. So if the concentration is equal to 10 to the negative pH, so we put in 10 to the negative, 5.3. And that gives us, you don't want to leave it in this form. Do put this into your calculator. We don't want decimals in our exponents. So expand this, and we get 5.01 times 10 to the negative 6 mole per decimeter cubed. Okay, so that's a couple of examples of calculating our pH. So we're going to look at another property, which is called the ionic product of water, which we use Kw. Now, anytime you see K with a subscript like that, think of your equilibrium constants, and that's exactly what this is going to be. So water molecules dissociate naturally. Okay, so there is an equilibrium within water, but it only dissociates to a very small extent. This is known as the auto-ionization of water. So it auto-ionizes by itself. Okay, so water splits apart into H plus and OH minus. Now, because this is an equilibrium, okay, this is constantly going back and forth, we can write an equilibrium constant for this. So our equilibrium constant, we write our Kc or our Keq, is going to be equal to our concentration of hydrogen times our concentration of hydroxide over the concentration of water. Now, this equilibrium, again, as I said, lies very, very far to the left. So if we just assume, so the concentration of water, we can assume pretty much stays constant, and we'll make another assumption that we just are dealing with a concentration of 1. And if that stays constant, we can then rewrite this expression as what we call Kw, which is just the concentration of protons in solution times the concentration of hydroxide. Again, that's because this water stays fairly constant through the whole thing. So we just assume that it's 1, it doesn't change, and we get this formula, which will become a useful one to us. Okay, again, known as Kw, or the ionic product of water, which is just all it is, again, is an equilibrium constant for water. Now, being an equilibrium constant, we know that it has to be a specific value at a specific temperature, and that it is temperature dependent. So changing the temperature does change the value of Kw. So pure water at 25 degrees, though, the hydrogen ion concentration and hydroxide concentration are both 1 times 10 to the negative 7. So the value for Kw at 25 degrees will be 1 times 10 to the negative 7 times 1 times 10 to the negative 7, okay, which equals 1 times 10 to the negative 14. Okay, so again, this is the Kw for pure water at 25 degrees Celsius. Okay, this is going to become a really useful number for us, which we'll use for a lot of various calculations. Now, since we know that the K is a constant, so Kw, if we write H plus times OH minus, that means that this product of hydrogen ions times hydroxide ions has to be equal to 1 times 10 to the negative 14 if we're dealing at room temperature. So what this means is that if the hydrogen ion concentration is to increase, then the hydroxide ion concentration has to decrease, because the two of them multiplied have to remain 1 times 10 to the negative 14. Okay, so there is an interplay between here, and we can use that idea to help us solve for pH and concentrations. Okay, so again, if one of these numbers increases, the other one has to decrease, or vice versa. A neutral solution, okay, is when they're equal. So although Kw changes its value at different temperatures, which means the product of H and OH will change, anytime these two are equal, regardless of number, that means we have a neutral solution. An acidic solution is when there's a greater amount of hydrogen ions, and a basic solution is when there's a greater amount of hydroxide ions. Now, that equation I mentioned before, if for a second we were to take the log of both of these answers, or both of these sides, let's take the negative log for a second to see what happens. So if we apply some log rules, we would have negative log of the concentration of H plus the negative log of the concentration of OH minus equals the negative log of 1 times 10 to the negative 14. And what that gives us, I'll write over here, negative log of H we know as pH, negative log of OH we know as POH, and the negative log of 1 times 10 to the 14 is just 14. So this is where that other equation I mentioned earlier comes from. It's just derived from our equilibrium constant expression for water. So we can use this one or this equation when solving problems. Either or is fine. And speaking of solving problems, let's try a few. Okay, so the first example here, the pH of a soapy water was tested and found to have a pH of 9.4 at 298 Kelvin. Calculate the concentration of hydrogen and the concentration of hydroxide. So since we're given the pH, we can calculate the concentration of hydrogen ions directly from that. So 10 to the negative pH, which gives us 10 to the negative 9.4, or 4.0 times 10 to the negative 10 moles per decimeter cubed. Now for this next part, now we need the concentration of hydroxide. So you can do this in one of two different ways. The first way is we can use our Kw expression. Okay, so our Kw we know is 1 times 10 to the negative 14 at room temperature. And our concentration of hydrogen we just found is 4.0 times 10 to the negative 10 times our concentration of OH minus. So if you are to rearrange this, so we divide by our 4.0 times 10 to the 10, we end up with a hydroxide ion concentration of 2.5 times 10 to the negative 5 mole per decimeter cubed. Okay, so that's one method, is just use your water constant, your Kw, to solve for it. The other option is we have our pH, so we could first convert to POH. So we know our pH is 9.4. So we can do that subtraction, and we get a POH equal to 4.6. Then we can find our concentration of OH ions by doing 10 to the negative POH, which would be 10 to the negative 4.6, which gives us the same answer of 2.5 times 10 to the negative 5 mole per decimeter cubed. So it doesn't matter which route you want to take. You can use either method. They'll end up with the same answers. Okay, so the last example here, calculate the pH of a 0.1 molar solution of calcium hydroxide, assuming complete dissociation. So before we start this one, since we're not given the concentration of anything directly, let's start with writing our dissociation equation. So calcium hydroxide is CaOH2. We're assuming complete dissociation in water, so that's going to become calcium 2 plus 2 OH minus. Now, since we have 2 hydroxides for every 1 calcium hydroxide that's dissociated, that means our concentration of hydroxide is actually going to be 2 times the concentration of our calcium hydroxide. Okay, or 2 times 0.01, which is 0.02 moles per decimeter cubed. Okay, so you want to be careful. That's why it's important if you're not given the concentration of hydroxide or hydrogen ions directly, you do want to make sure to write your equation to make sure you're getting the correct amount. Now that we have this, again, you can choose either method. You can calculate the pOH or figure out the concentration of hydrogen ions from this value, because our goal here is to find pH. I want to calculate the pOH, which is minus the log of our concentration of hydroxide. So we get minus the log of 0.02, which gives us a pOH of 1.7. Okay, and then we can calculate our pH, which is 14 minus 1.7, which gives us 12.3. Okay, and that brings us to the end of our pH calculations. We'll look at some more complicated ones when we get into the advanced section of acids and bases, but this is it for now.